After completing the CFD study and connecting between the acoustic mesh and the CFD mesh, we began to make a linearized Navier-Stokes study. Okay, so we can see the influence of the fluid flow on the acoustic wave coming from source here. So first we need to set up the acoustic model solving the linearized Navier-Stokes equation for the background mean flow configuration with Mach equal 0.05 and Mach equal 0.1. The no flow case will be Mach 0 equals 0 will be solved as a pressure acoustic study, separate one. And first we create variables and set up the PML, perfect meshed layer. So first here we go to definitions and then variable. We have the source here, plane wave, and then here. So we have here the variables. First variable is convected wave number of the wave, and then the background field, pressure, and then no velocity here, no velocity in y or v, just we have velocity in z, and then the temperature. Another definition here is the integration. We will integrate from non-local group integration. We will call it in top integration operator n. And then we're gonna integrate in the setting window for source selection. We choose here boundary. From the boundary, we choose only boundary number 6. So here we can find the pressure wave here, and we can find pressure acoustics and different aspects related to integration. The integration method is integration with order for spatial XYZ. Okay, so then we have another integration from definition, non-local coupling, and then integration. We call it in top out, and we put that in the beginning of the second domain because the linearized Navier-Stokes equation will not solve for 1 or 9 because there will be a PML, perfectly meshed layer. We will choose the 18 boundary. So we will integrate in the inlet and outlet of the acoustic domain. Then we will add an artificial domain. We call it perfectly meshed layer, and this perfectly meshed layer is used here for non-reflecting waves because in the end and the beginning of the domain the waves will come here and here, and then it will be hardly to detect if there is a reflected wave from outside the domain. So we put a perfectly meshed layer for preventing the reflected wave coming from out the domain. Okay, now we are ready to go to linearized Navier-Stokes equation model. Inspect the model here, close all these. Go to linearized Navier-Stokes equation model. We can see here it's linearized Navier-Stokes equation frequency with LNSF, linearized Navier-Stokes frequency. The equation, this is all the domain equation, and the reference value for C is 343 for air. Okay, we go here to linearized model. Okay, in the model input we notice that mapped pressure here and mapped velocity also here. So we go to wall, and then for mechanical condition we make it slip condition. For thermal condition we make it adiabatic condition because we don't have like heat transfer and we want to make it real, so slip condition is okay. We will have like a symmetry here, and the symmetry from selection we choose symmetry boundaries. We will not here that everything that called perfectly meshed layer he will not solve for it. And then we go here and choose background acoustic field. This is the plane wave that we just said. Locate the background acoustic field here, and then we put here BB, UB, and VB. That's okay, and then here we say WB. Finally, we put the temperature of TB. Okay, so for the selection 2, we choose domain 2 only, as this is the domain that will give or will have the background acoustic field. Then linearizing the Navier-Stokes equation is ready. So we're gonna study. We have add a new study. From here, we will later check for background flow and turbulent flow, and just only for solving for linearizing the Navier-Stokes equation. And then we add frequency domain study, and then we add it. So study number 3 here is the frequency domain study of the Navier-Stokes equation. We will call it Navier, linearize it, Navier-Stokes frequency domain for Mach number equal 0.05 and Mach number equal 0.1. So we are here in the frequency domain. We should first choose the range of frequency. So the frequency note is hertz. The range of frequency, we're gonna start from 50 with a step of 10 to 200. And this range is like depend on the problem. You'd like to expand the value of dependent variable. Of variables not solved for. Okay, so we user control and then solution. We're not gonna solve it. Then we choose mapping. For Mach number, choose automatic, means all. We're gonna see it's acoustic mesh. And we're gonna do like add in the study extension. We will add 2 studies in the auxiliary sweep. For Mach number equal 0.05 and Mach number equal 0.1. So he will make 2 studies. In our uncontinuous for we say manual, and then continuous parameter is frequency. We return back to the study and clear general default plots. We go to solver, default, show default solver, change some solver default. We go to stationary solver. That will be solved for. This is enable here, and then we start to compute. After completing this study, we will go to solve the no fluid case with pressure acoustics. After completing the study, we go to demonstrate results. First, we go to the results of pressure acoustic, Mach equals 0. So we start here to have 3D plot, and from the 3D plot, change the name to be acoustic pressure Mach equal 0. In the dataset, we choose study number 4. In the frequency, we study like 150, middle frequency. Selection, just the domain. It's here 3, 4, 5, 7, and 8 to apply to data edges. Apply to dataset edges. This is the domain that we wanna. Okay. The surface from parents, everything from parents. The expression, what we want to demonstrate on this domain. This is the velocity, as we see. We don't want to have a velocity. We want to have a pressure acoustics. So we go here. We have a pressure acoustic frequency domain. Total acoustic pressure. In the color table, choose wave. In the wave, we choose symmetric color range. And then we choose plot. So here we have the plot. We will do the same things for Mach 0.05 and Mach equals 0.1. So we can come here and duplicate this pressure, change the name to 0.05, and we will choose the study of Mach 0.05 and Mach 0.1. For Mach, we choose 0.05 and the frequency is the same, 1.50. Okay, the domain is the same, and 3, 4, 5, 6, 7, and 8. We go inside here in the surface, change the expression. This expression related to pressure acoustic, we change it to go to linearized Navier-Stokes equation, background, and scatter field, and then we have total acoustic pressure. Yeah, you can see this is some little difference. It's linearized Navier-Stokes equation dot P of t, and then we choose plot, and then we can see here this is one frequency 150 and Mach number 0.05. For the last one, and choose duplicate from 0.05, change the name to be 0.1, and then we change that to be 0.1, and we plot. You can see a little difference between 0.05 and 0.01. We can also plot the acoustic pressure sound level. So we go here, 3D plot, we type acoustic pressure sound level at 0.05. So we from here we have study number 3 on 0.05, and it's 150. From the selection, choose domain, here 2, 3, choose surface, and then from parent, in the expression, we choose here linearized Navier-Stokes equation, and then we go to acoustic, background and scatter field, choose total sound pressure level. Okay, it's with dB, which is decibel. Okay, choose the color table, which is rainbow. Okay, you can see here The reading difference between the pressure inlet level and the pressure outlet level. Pressure sound level is used to really identify the difference between the inlet and outlet. As we see, this is red, this is yellow, and then this is green. Okay. And then we plot the transmission line. So we have the 1D group, transmission loss. As we know, for transmission loss, 2 studies. So we're gonna just like identify the block only here. For X, we tell frequency, and for Y, we have the transmission loss. On the axis, the frequency from 50 to 200, and here Y from 0 to 40. Then we have a global. On the global, this is for pressure acoustics study. The expression we plot 20 log for absolute in top in for 1 Pascal over, like we represent the inlet pressure here on the outlet pressure, and we take the logarithm of 10 for it, and then we multiply that by 20 to make it decibel. And here is the outlet pressure, total pressure. Okay, we have here the first plot of transmission loss, color and style, marker. We put some points on data more visible. And the ligand here, we put it manual and write MA equals 0. So we have that MA equals 0 here. Okay. The other one, we can duplicate that here. Okay. But we change the study to Mach equals 0, Mach equal 1. And then we change that here the pressure inlet to be P of B. This is a bed pressure. Change the acoustic pressure to linearized Navier-Stokes pressure. And we choose any 0.05, 0.1. Then we plot. We have here, as we see, the transmission loss when Mach equals 0, the transmission loss when Mach equals 0.05, the transmission loss of Mach equals 0.1. We can see the maximum value here happens like in a value between 80 and 100. Here the maximum value in another place and maximum value in another place. That's why, because of the flow, the value of flow affecting the value of transmission loss, which means like the reducing in pressure from the second here to the first here. So we're gonna check that when we are designing the Helmholtz resonator for any system. What is that system flow rate, what we are working on, and how it affects the transmission loss. So what we need to have here, and finally the sound level, what we need here, or the sound pressure that we need here, and finally the final stage at that frequency. And thanks for watching, and I really appreciate if you subscribe and follow us here in this YouTube channel. Thank you.